Hello, and welcome to the presentation, CyTOF for All, the top 8 reasons to use mass cytometry for your project. While we will cover 8 reasons for using mass cytometry in your research, the 3 primary aims of this presentation are to provide detail on the ever-increasing use of CyTOF around the world, to provide the reasons why CyTOF has become so popular for high-parameter cytometry, and to clear up some misconceptions about the technology. As a preview, here are the top 8 reasons to use CyTOF that will be covered in more detail in this presentation. The first reason we will cover is that mass cytometry is a proven and well-adopted technology. Publications featuring mass cytometry continue to grow year by year since the technology was first introduced. The rate of new publications, indicated by the gray bars, shows a trend of increasing nearly 2-fold every year, proof that mass cytometry is becoming more accessible and widely adopted by many researchers. A breakdown of these publications that feature mass cytometry and their areas of study is shown on the left. Much of the research comes from the fields of immuno-oncology, oncology, and basic immunology, but also extends to stem cell biology, neuroscience, infectious disease research, and data analysis approaches. The graph on the right shows the distribution of panel sizes used in these studies. A third of mass cytometry published panels were in the teens to 30 marker range. Over half of these studies use panels of 31 markers or more. Overall, based on the breadth of literature available, mass cytometry has diverse applications and great flexibility in the number of markers that can be used. There is also growing adoption of mass cytometry in clinical trials. As of January 2020, there were 67 ongoing trials citing mass cytometry as a readout, with the bulk of these trials using mass cytometry for phase 1 and/or phase 2 clinical research. 8 trials using mass cytometry have concluded. Additionally, 23 observational trials are making use of mass cytometry for a total of 75 clinical trials that filed with mass cytometry as a readout. This information has all been sourced from clinicaltrials.gov. Much like the discussion of publications, we take a look at the research areas of these filed clinical trials. We can see that the immuno-oncology field dominates. However, there are also trials looking at surgical outcome, infectious disease and vaccine trials, and autoimmunity, in addition to other assorted clinical investigations. The second reason is that mass cytometry has performance equal to or better than fluorescence cytometry. I will highlight 2 key publications that support this. The first publication discusses the use of mass cytometry as a potential readout in clinical research. Gadala et al. Compared a single tube 40 marker mass cytometry panel side by side with a multi-tube 8-color flow cytometry workflow on human PBMCs and dissociated tumor. Their key findings show a statistical congruence in the populations using both approaches. Both methods also showed comparable staining quality and signal intensities. The authors emphasize the ability of mass cytometry to identify phenotypic, functional, and exhaustion markers in a unified manner as an advantage over a multi-tube workflow. The authors also point to mass cytometry's superiority in the discovery of new biomarkers and for getting the most information from limited and precious samples, such as tumor biopsies. The next publication is a review article from the IRI and Irish labs at Vanderbilt University. Mystery et al. Reviewed the utility of various technologies to analyze solid tumors. Their observations led to the conclusion that mass cytometry serves as one of the most capable approaches, bridging the high parameter yield of single-cell RNA-seq and the throughput cost-effectiveness of flow cytometry. The authors argue that mass cytometry is a method that has great utility in driving advances in the tumor biology field, unified proteomic analysis, as well as the capacity to identify rare cell types. In addition, the authors mention that CyTOF technology can also be used to integrate spatial information in studies of the tumor microenvironment through the Hyperion Imaging System. I wish I had even more time to review some of the key findings of these publications with you. However, in the interest of time, I will suggest that you review the list of publications here, which give a good overview of mass cytometry, how it compares to flow cytometry, as well as two publications specifically focused on less well understood aspects of fluorescence cytometry, namely spreading error caused by fluorescence subtraction and basics on how spectral cytometry works. Number 3 is the simplicity of CyTOF. In this section, I will discuss how the Helios mass cytometer is a straightforward instrument for daily use. The Helios mass cytometer uses the well-established technology of inductively coupled plasma mass spectrometry while handling the sample preparation, sample introduction, and data output in a manner similar to flow cytometry. Using this approach offers a variety of advantages. First, the Helios is a single detector system with a direct path from cell ionization to signal detection. Only one daily QC, called tuning, is needed for system calibration and optimization. No assay or metal-specific adjustments are required. No compensation or single-stain controls are needed. Second, there is no impact of autofluorescence on signal sensitivity. Mass cytometry has nothing analogous to autofluorescence, since the metal isotopes that are used as tags do not occur naturally in biological systems. From a workflow standpoint, mass cytometry is considerably less complex than any high-parameter flow cytometry approach. This slide shows the simple and straightforward workflow for initializing the Helios for daily use. The system warms up for 30 minutes. Next is an automated daily QC and system optimization. At this point, the system is ready for sample acquisition. Note that there is no assay-specific optimization steps prior to sample acquisition. Several tools are available for use on the Helios, which enable streamlined, standardized analysis. First is daily QC, called tuning, which provides automated instrument calibration and optimization. Second is data normalization, a standard procedure for mass spec instruments performed using a spiking control bead and CyTOF software. The third is barcoding. Mass cytometry is the only high-parameter cytometry platform which enables barcoding. Fluidigm's barcoding kit allows staining of up to 20 samples each with a unique 3-digit palladium code. Barcoding is a unique and highly valuable application that eliminates tube-to-tube variability when staining, reduces reagent use, saves time during both sample preparation and acquisition, and enables better single-cell discrimination. The fourth reason to use mass cytometry in your research is the easiest high parameter panel building you will ever experience. In this slide, you'll see the emission spectra for violet laser excited dyes in the 20-color flow cytometry panel. This illustrates that there is significant overlap between emission spectra of fluorescent tags. This overlap reduces overall sensitivity in channels where it occurs, requires multiple control tubes of sample, makes it difficult to use over 20 fluorophores routinely or to change the panel later, and requires more iteration when building high parameter panels than mass cytometry. Fluorescent cytometry signals are also impacted by autofluorescence even when the autofluorescence is subtracted, which leads to sensitivity reduction, and can make co-expression difficult to parse out. In addition, compensation and spectral unmixing is affected by instrument configuration and settings, as well as the use of appropriate controls. In contrast, Helios has 135 truly distinct channels for signal detection, which makes building a high parameter panel quite easy as compared to flow cytometry. Assay-specific optimization and compensation are not needed in mass cytometry. Let's take a look at a 22-marker surface-only immunophenotyping panel in mass cytometry and flow cytometry. The left-hand column of the table shows the markers, while the two columns next to the markers shows the corresponding metal tags in the middle column and fluorochromes in the right column. Please note that for the mass cytometry panel, we are only using half of the available metals that can be incorporated into a mass cytometry panel. The graphic to the left identifies the subsets identified by either panel. Here is an example of a spillover matrix for a Cytek Aurora panel for the fluorochromes chosen for the panel in the previous slide. This matrix was created using Cytek's own full spectrum viewer at spectrum.cytekbio.com. This matrix assumes that there is equal expression levels across the markers in all channels. While this is never the case in biology, it does illustrate the care needed in placing high or low expressing markers in certain channels. This process is challenging and leads to highly iterative and restrictive panel design. We created a mass cytometry panel with the same assumption of equal expression of all markers in all metal channels. Note that there is little to no spillover between metal channels. For this reason, compensation is not necessary for mass cytometry panels. Spillover in mass cytometry is predictable and constant, as well as independent of instrument settings. This not only allows for easier initial panel design, but also the freedom to modify an existing panel without the need to start from scratch, which is often the case with flow cytometry panels. Here is a real-world comparison of flow versus mass cytometry recently demonstrated on a poster from the University of Rochester at CyTOF 2019. To summarize, the authors found it comparatively easier to design a 32-marker panel for mass cytometry compared to flow, and also saved time and ran fewer samples optimizing the panel. The fifth reason to incorporate mass cytometry into your research is that it provides the most capable high-parameter cytometry available. Lower dimensional fluorescence cytometry of 15 or so parameters enables a broad range of applications. However, an evaluation of the 7 optimized multicolor immunophenotyping panels, or OMIPs, with 20 to 30 parameters shows that the predominant application is surface phenotyping, and in some cases, a few intracellular markers for phenotyping or function, such as cytokines or cell death and apoptosis, have been included. The exact technical reason for this is unclear. However, for mass cytometry, the range of proven applications is quite a bit broader. In addition to the range of markers established in the flow cytometry OMIPs, mass cytometry has enough open channels to allow combination of broad phenotyping along with other applications such as signaling, cell cycle, epigenetic markers, and tetramer studies. In fact, multiple publications utilizing mass cytometry with barcoded tetramers has enabled the investigation of hundreds of epitopes simultaneously. As shown in the image here from Gonzalez et al. In Cell Reports, mass cytometry allowed assessment of not only surface phenotyping and functional molecules, but a large number of intracellular and intranuclear signaling molecules, all in a single tube of a digested ovarian tumor sample. There is an extensive bibliography of papers using mass cytometry for similar analyses. The very limited number of publications using high parameter flow cytometry incorporating signaling, cell cycle, or histone staining shows it is much more challenging to perform these kinds of functional analyses by fluorescence, probably due to the increase in autofluorescence cells undergo during the harsh staining conditions required, or perhaps because certain fluorochromes are sensitive to such fixation. One of the major strengths of metal-labeled antibodies and other metal tags is that they are robust. Unlike many fluorochromes, metal tags are resistant to harsh staining conditions such as methanol permeabilization, do not photobleach, fall apart, or interfere with each other. Labeled cells can also be frozen and stored at -80 with little to no impact on staining quality. Fluidigm offers 42 metals available in kits to easily label antibodies of your choice. And finally, barcoding. Mass cytometry is the only high-parameter cytometry platform which enables barcoding. Fluidigm's barcoding kit allows staining of up to 20 samples each with a unique 3-digit palladium code. Barcoded samples are then combined and stained, processed, and acquired as a single tube. The single barcoded FCS file is then debarcoded with the debarcoder in CyTOF software to create single FCS files for each original sample. Barcoding is a unique and highly valuable application that eliminates tube-to-tube variability when staining, reduces reagent use, saves time during both sample preparation and acquisition, and enables better single-cell discrimination. Now that we have covered mass cytometry applications, let's discuss the excellent array of reagent and antibody options available. Reagents are one of Fluidigm's tools for streamlined, standardized analysis. First, Fluidigm sells a total of 22 panel kits, many of which are designed to be combined together to create large panels. The range of applications covered by these panels is shown in the table on the right and includes general immunophenotyping, more targeted phenotyping of certain cell types such as T cells, B cells, or myeloid cells, as well as functional panels for cytokines, signaling pathways, and cell cycle analysis. There are also panels devoted to checkpoint markers as well as in-depth immune monitoring. Fluidigm also offers a large catalog containing more than 750 pre-conjugated antibodies, as well as labeling kits with a choice of 42 metal isotopes to conjugate your own antibodies of interest. Our custom conjugation services allow our in-house experts to label antibodies for you if you prefer. Lastly, Fluidigm's panel design tool is an excellent aid in designing or modifying your mass cytometry panels. Now I would like to elaborate on how our panel kits can be easily combined into larger panels. The example shown here is the Maxpar Human T-Cell Phenotyping Panel Kit. It includes 16 markers strategically placed on the 44 available metal channels. This panel by itself identifies naive and central memory subsets, terminal effector and effector memory subsets, as well as homing and activation status in both CD4 and CD8 T cells. Note that there are still 28 available channels. To the 16 marker T-cell phenotyping panel, we can now add the 10 marker T-cell expansion panel kit. These added markers enable identification of additional T-cell subsets, naive and memory regulatory T cells, as well as Th0, Th1, and Th2 subsets. There are still 18 channels available. Let's go even further. The previous two panels can be combined with the Maxpar Human T-Cell Immuno-Oncology Expansion Panel Kit. This panel kit provides antibodies for 8 key markers of checkpoint response: ICOS, CTLA4, PD1, TIM3, LAG3, 4-1BB, OX40, and FAST. By combining these 3 panel kits, we now have a 34 marker panel which enables deep profiling of CD4 and CD8 T-cell subsets and functional markers. 10 open channels still remain for further customization. We have discussed performance, applications, and tools. Now let's discuss reason 7, mass cytometry's unrivaled data quality. Profiling the human immune system is a key application used in translational and clinical research to look for biomarkers of disease or response to therapy. It is essential in driving the search for more effective treatments for almost any disease: cancer, autoimmune diseases, or infectious disease. Fluidigm has created the Maxpar Direct Immune Profiling System, which was named the best new cell biology product of 2019 by the Life Science Industry Awards. The Maxpar Direct Immune Profiling System is a truly revolutionary approach to immune monitoring and is absolutely unique in the cytometry market. The system consists of an assay kit with a dry 30-marker panel in a single tube plus reagents needed to process either human PBMC or whole blood samples, a custom template to collect the samples on a Helios mass cytometer, and an automated data analysis software solution, Maxpar PathSetter, which identifies 37 immune cell populations in as little as 5 minutes. An associate professor of medicine and oncology at a major U.S. comprehensive cancer center noted, "We are very eager to start using this kit in our translational studies. In our test, the Maxpar Direct Immune Profiling System showed high intrasite reproducibility, minimal intersite variability, and gave robust immunophenotyping performance." A peer-reviewed publication in Cytometry B detailed multi-site reproducibility of the Maxpar Direct Immune Profiling assay coupled with Maxpar pass setter software. Replicate samples of PBMC and whole blood from single donors were stained and acquired at 6 or 7 sites, respectively. Analysis was performed on-site with Maxpar pass setter software to enumerate cell population frequencies. Key findings in the paper showed a high degree of reproducibility for the cell population frequencies identified in PBMC and whole blood. This was found for both inter-site and intra-site results. These findings affirm that the Maxpar Direct Immune Profiling Assay is a convenient and reliable solution for deep immune profiling at any institution or across multiple sites. And lastly, number 8 is community. If you are new to mass cytometry, you are not alone. Mass cytometry has a very supportive global community. Mass cytometry has a strong global community of users and resources. Publications are available to explore through the Fluorescence bibliography, in addition to several mass cytometry OMIPs and a book devoted to mass cytometry methods and protocols. There are also many data analysis resources. Fluorescence has a team of expert field application specialists ready to provide direct support. Additional support and interaction with the CyTOF community is available at regional user group meetings and the annual Mass Cytometry Summit. The independently curated CyTOF forum is available to the global mass cytometry community as well. CyTOF technology is also being adopted widely in multiple consortia-driven projects, such as the 10,000 Immunomes project. We would invite any attendee here to experience the mass cytometry community by registering for the 9th annual Fluorescence Mass Cytometry Summit, which will be held virtually this year. Please register today at fluorescence.com/summit2020. Dates for the virtual summit will be announced soon. In summary, we have covered 8 reasons why mass cytometry should be used to advance your research. These reasons are proven, performance, simplicity, easy panels, high parameter capability, an array of reagents, data quality, and community. Before I close out the presentation, I wanted to mention another significant and unique advantage of the Helios, the ability to do high-dimensional tissue imaging. An existing Helios system can be upgraded at any time with a Hyperion tissue imager to create the Hyperion Imaging System. This approach allows for the deep profiling of formalin-fixed, paraffin-embedded tissues, frozen tissues, or cytological preparations on standard glass slides at subcellular resolution while preserving the contextual information in tissue architecture and cellular morphology. Today, researchers are using imaging mass cytometry to discover new biomarkers, explore the tissue and tumor microenvironment, and understand biological mechanisms and cellular interactions within the spatial, structural, and contextual information of a tissue sample. This compares to just a few markers per sample that can be assessed at any one time with conventional immunohistochemistry. The Hyperion Imaging System brings you unrivaled multiplex imaging with clear leadership in this field through greater than 80 system placements around the world, over 45 peer-reviewed publications, and more than 100 antibodies for use in frozen and FFPE tissues. Imaging mass cytometry, or IMC, is also being used in clinical trials. In addition, there's a simple way to get started with the ready-to-go immuno-oncology IMC panel kits. And as mentioned earlier, the Hyperion Imaging System is the only high multiplex imaging solution available with dual mode capability to analyze cells, whether as tissues or in solution from the same instrument. Dual mode with the Hyperion Imaging System enables high multiplex characterization in both cell suspensions and tissue samples. It is convenient to switch from cell suspension mode to tissue imaging mode. This can improve return on investment by increasing utilization and diversifying sample throughput. But more importantly, the ability to study both cells in suspension as well as tissue can drive comprehensive insight into health and disease. For translational researchers who are currently using mass cytometry, dual mode offers the same high multiplex capability that is found in suspension mode, but in imaging, deep spatial characterization of tissue microenvironments, and comprehensive data sets that contribute to greater research insights. Dr. Kevin Kelly, the Assistant Medical Director of Clinical Investigations at the University of Southern California, noted, the Hyperion Imaging System offers the capability to assess the characteristics of both circulating and tissue cells in a multiplex manner, offering a substantial return on investment for the cancer researcher. Thank you for attending the presentation.